So we have been talking about these enthalpy cycles using Hess's law to find different enthalpies of things that we can't empirically measure. And we've learned about a bunch of different ways to do that with bond enthalpies, with enthalpies of formation, enthalpies of combustion. We have one more that you need to learn, and it has to do with ionic compounds. So we don't have bond enthalpies for ionic compounds because there's not a covalent bond there. All right, so there's something sort of similar, though, that we can talk about, which is lattice enthalpy or lattice energy. And that's basically what is the energy that is released when we take ions and we put them in an ordered solid array where the forces of attraction and repulsion, forces of attraction are maximized, forces of repulsion are minimized. This is going to be a very stable, low energy state, okay? So going from ions to the lattice structure is going to actually release a lot of energy. And we've already seen that because that is how these hand warmers work, the reusable ones. Okay, so the energy that we're getting from those hand warmers is essentially the lattice energy of the formation of that crystalline compound. Okay, so that is sort of a new thing to add to our bucket here. And we'll talk a little bit more about it when we review bonding, which will happen, I'm not sure exactly when, later. For our purposes right now, you just need to know that this is essentially another piece to the Hess's law puzzle that we can use for ionic compounds. So if you look at page 6, there's this very long list of things that looks just awful. And then there's this big chart here, which looks like, oh my God, what is going on here? Okay, basically, page 6 is giving you all the pieces of the chart on page 7. Okay, and so I'm going to walk through them with you, but the idea is that we can create this really big enthalpy cycle in order to calculate. Usually you'll be calculating either the lattice enthalpy of an ionic compound or its enthalpy of formation. So you're usually going to know one of those and then all the other stuff. And so it still really is just solving for one thing and figuring all the other ones, or figuring out how to put all the other things in there. Okay? So don't be intimidated by this. You've done this already. It's just on a slightly bigger scale and a little bit different. So let's just kind of look at the diagram first, because I think it's actually easier to look at that than it is to read all the words and go through all the different parts. So at the bottom here, we've got our solid sodium chloride. That's the lowest energy state that these two elements can be in together, basically. So that's going to be at the bottom. We've got our lattice energy that would basically, in this case, it's going up. That's really how we think about the lattice energy, or lattice enthalpy is that how much energy it would take to break that solid crystal down into its component ions, and specifically gaseous ions. That's the real definition of the lattice enthalpy, which we'll see on the. It's written on page 6, but that is the enthalpy. So honestly, in terms of the strict definition, what we had coming out of the hand warmers was not exactly this for our sodium acetate because they weren't in gas form. But we could have built something like this for that reaction. Okay, so then, but let's go back to the other side. So the enthalpy of formation here is just the same as it is for other substances. You learned how to write enthalpy of formation equations, and it's basically the elements in their standard state, enough of them to make up 1 mole of the substance that you're making. So in this case, our sodium is just going to be solid sodium. Our chlorine is going to be one mole of chlorine. So, but chlorine is a diatomic, so it's going to be half a mole of Cl2 in the gaseous state. Okay, so that's going to end up being the thing that we're going to be calculating in this particular cycle, is the enthalpy of formation. So this is our question mark, okay? That's what we're solving for. If you then look here, the next level going up is we've got to take our solid sodium and turn it into a gas. So there's a certain amount of energy that we're going to call the enthalpy of atomization that takes the sodium from a solid to a gas. Okay? And then we also need to separate out our chlorine atoms from our diatomic. Okay? And this is essentially going to be our bond enthalpy. But it's going to be half of the bond enthalpy for Cl2 because we only have half a mole going down here into our NaCl. So this is taking our 1/2 Cl2 and turning it into just neutral chlorine atoms. Okay? So this is going to be bond enthalpy. Now what we need to do is turn them into ions, because we have to get them into ions in order to get them to the lattice state here. So we're going to take our sodium and we're going to lose an electron, and that's going to be our ionization energy. That's something that you learned about in honors chemistry, the energy required to remove 1 mole of electrons from 1 mole of neutral atoms in the gas state. So we're already in the gas state, which is good, okay? And then something we don't talk about in honors chemistry, but what is basically the opposite of ionization energy, is something called electron affinity. And that is the energy released when 1 mole of gaseous neutral atoms takes in 1 mole of electrons. So adding electrons rather than removing them. And that's what we're going to do for the chlorine. So the chlorine is then going to become Cl minus. Ionization energy is always positive. Electron affinity generally, well, in this case, it is negative. And that takes us to the point where we can then talk about the lattice enthalpy. Okay, so if we have that value, we can then go from here to the bottom, and now we have everything except our enthalpy of formation, which is what we're solving for. Okay. I want to go back to page 6 and just kind of walk through each of those different things now that you kind of know where they fit into the puzzle. So this whole thing is called a Born Haber cycle. And it's usually, like I said, it's used to calculate either the lattice enthalpy or the enthalpy of formation. Ionic compounds only, okay? Covalent compounds are easier because we can use bond enthalpies and other methods. So what is lattice enthalpy? Again, enthalpy change when 1 mole of solid ionic compound separated into gaseous ions under standard conditions. And by standard conditions, really they mean standard pressure, because you're not going to be able to do this at like standard temperature. I mean, you're going to need to add a lot of energy, so it's probably not going to be standard temperature, but essentially that gives us the plimsoll next to the delta H. And so we can see that lattice enthalpy for sodium chloride is 790 kilojoules per mole. So let's go add that to our figure. So this is 790 kilojoules per mole. I'm gonna put the signs on there, but as you're gonna see, that's actually not gonna be the important aspect of this. It's positive because the arrow is going up, okay? Okay, so endothermic has a positive value. Then we have our standard enthalpy change of formation, which you already know. Okay, so this is the thing that we're solving for. So this is forming from the elements in their standard states under standard conditions. Okay. So that, again, that's our question mark. Enthalpy of atomization is when we have 1 mole of gaseous atoms formed from an element in its standard state. So that's going from for our sodium, that's going from the solid state to the gaseous state, and that's 107 kilojoules per mole. So we're going to put that on here. That is 107. I'm going to leave out the kilojoules per mole on all of these just because it doesn't, there's no point in writing them in unless if you're being asked to annotate a diagram on a test, then you would probably want to write the units in or at least have it somewhere on the graph, but it's not really important for this. Okay, now you'll see that there's this enthalpy of atomization, and then there's also this thing called enthalpy of sublimation. And they're exactly the same in this case for sodium. There is a slight difference here. So this is element in the standard state. This is solid state. Okay, so if the standard state may not be a solid in some cases. It might be a liquid, for example, if it's bromine. So the reason these are exactly the same is that the standard state for sodium is the solid state. So this is just, I think what he's trying to do by including both of these is just to point out that depending on the element, you might use one or the other to get to the point where you have gaseous atoms. Okay. But we don't have a separate thing here. Oops, sorry, for enthalpy of sublimation because it's the same thing. So we can just put, in this case, either way. We can think of it either way. It gets us to the same place, and it's going to be the same number. Okay. Oops. Okay. First, ionization energy. Energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. That's why we needed everything to be in a gas form. So again, for sodium, we are removing electrons. So that's our ionization energy is 496. So this is our 496. Okay. And that gets us through everything for sodium. Okay. So going back to chlorine now, we were already in the gas state because that was our standard state for chlorine was diatomic gas. So we then need to look at the bond enthalpy for that, taking that from the diatomic into individual atoms. And so it's 242 kilojoules per mole. But because we only have half of that here, we only have half of a Cl2, here going to the chlorine atom, or mole of chlorine atoms, we're going to divide this by 2. So okay. So 121 is what we're going to put on our chart, okay, because we're only doing half of this. So this is going to be 121. Okay. So that takes us to our neutral chlorine atom, which then we have to add an electron to. And this is our electron affinity. So this is, again, kind of the opposite of ionization energy. Kind of. In that it's The electron is now on the reactant side instead of on the product side, and we're ending up with a negative ion instead of a positive ion. So this electron affinity is going to be negative 349. Okay, so we're going to add that. Okay, so what we have here are all of the pieces to get us to our enthalpy of formation. The question is, how do we put them all together? Okay, and this is where one of the questions in the exit ticket, a lot of folks got wrong, and I think that this will help you understand why, but we will go over it tomorrow. It doesn't matter that this is negative and this is positive and those are all positive for the purposes of this calculation, okay? Because what we're saying is that everything over here, going from bottom to top, or top to bottom, either way, the sum of these is going to be equal to the sum of these, because they're starting in the same place and going up to the same place. Okay, so so we're just gonna and we're gonna add the absolute values, because it's not the direction of the arrow that matters here, it's the distance. The distance being energy or enthalpy, okay? So our y-axis here is basically enthalpy, okay? And so we're going to add these up. The absolute value of all of these is really what we're adding up, okay? Because it's the distance, not the direction, that matters, which makes this different from our other enthalpy cycles, okay? So we take our numbers and we say 349 plus 790 is going to be 1139. That means that this also has to equal 1139. Okay? So our 496 plus 121 plus 107 is 724. So our delta HF is going to be 1139 minus 724. Okay. So it's this whole value minus this whole value gives us this value. Okay. I'll just do the okay. So that we're saying that this minus that, I should actually change this to be more here, because that's what we're solving for. That's our unknown. Okay. At the end is where you're going to need to look at the arrow to figure out the sign. Okay, so if you're solving for enthalpies of formation, your sign's going to be negative. If you're solving for lattice enthalpy, your sign's going to be positive. Okay. So, hi. Ooh, cool. Oh, it didn't turn out too badly. Yeah, all right. I did the glaze and sip. So I have caffeine and theobromine on here. And this is my sister's. Awesome, thank you so much. I appreciate the delivery. Yeah, my sister did a cool day-night thing. So, awesome. I know they're going to do it again. You guys should do it. It's fun. But then again, you guys get to take ceramics as a class. I kind of wish I could. Okay, does this make sense? Is there a piece of this that you are not getting that you're like, how did you get that number, or where did this come from? Yeah, Jacob. Yeah, because like I said, we're not looking at the sign, we're looking at the distance for calculating it. But then at the end, you have to go back and address the sign for your final answer. So this is going to be negative because the arrow is going down. Okay? And this is going to be in kilojoules per mole, because that's what all of these things are in. Okay? If you were solving for lattice enthalpy, you do the same process. It would all be absolute values, but then your number, because it's going up, would be positive. Okay? Okay. I am going to ask you guys to do example 2 or question 2, which is on the next page. Here are all of the pieces that you have. Again, you're calculating delta HF. So this is your question mark. Okay. Feel free to talk through it with your peeps. Oh, you know what? I missed something. I missed something? Oh, no, I didn't. Never mind. Hang on. Let's go back. Yep. Okay. Okay. So this, if we're taking, what we're trying to do is go from here to here. This is what we want to be able to compare it to. That's what we have over here, the 2162 data. So what? And then back up here. Okay. So you're actually going to flip that way you did on there. And then I think you should be good. So this, you already have the 1145 here.
Oh, okay.
So this is, yeah, this is, right. So, oh, I see what you're doing. Okay, I kind of see that, yeah. It's not quite there, though. Oh, because this, going from here to here, the oxygen to the O negative, that's your EA1, this. And then your EA2 is this. See if that, you can, but you're close. You're close.
Because I can't
Yeah.
tell.
Yeah, no, you're close also. Okay. So this, think about, you know what, I'm gonna talk about this on the board in a second, but you're, getting there.
Oh, so is this negative or positive? Is it negative because it's going down?
Yeah, negative because it's going down. Yeah. Yeah.
So, would I add these three or just these two?
So think about it as you're trying to get this or something like this to be equal to this, or find out like how you can get to here. So this is taking you all the way up here. Here you're kind of going down, right? Because to go from here to here, you're subtracting, okay? And then going from down here to up here, you're adding. So that's what you're going to do with those two numbers to get it together. Hey guys, let me address something that I think a couple of you figured out, but it's tricky, right? Because this added a new twist, because we've got this thing where our lattice enthalpy doesn't take us all the way up here. We've got this little weird shenanigans going on up in the corner here. So what we're trying to get to is for this side, this whole thing really, to be equal to something over here. But we need to sort of bring this across, okay? So we can't use the entire lattice enthalpy, okay? Because that's going to be too high. So we have to figure out how to incorporate our electron affinities. And if you think about it, we're here and we want to go there. So we're going to have to go, down here and then up here to get to that spot. Okay? Even though, just in terms of the cycle, not in terms of the actual values of these, the signs of these numbers, okay? So in terms of the cycle, we're going to have to subtract here and then add here. And in order to get this side equivalent to this side, essentially. So we're going to have to take our lattice enthalpy, subtract our EA2, and add our EA1. Okay, and that's going to get us to the same level as what we have over here. So take another minute and see if you can incorporate that into your calculation. So you're going to take this, subtract this, and add that. And then that can be set equal to this. Good. All right. So that's the answer. If you get this, you're correct. If not, I'm going to stop the recording, but I'll come around and check in and see where you're missing something. So that's what you're trying to get to using all of these numbers. I will say before I stop that you're not going to have to build one of these, okay? So you're not going to have to figure out how to put one of these things together. The most you'll have to do is what you're doing right now, which is evaluate one and find the missing piece. And I don't know what the chances are of this being on the test. There are some things in the question bank that have questions like this, and I'll show you one of them in your exit ticket that I'm giving you tomorrow. All right, so tomorrow we're going to go over any enthalpy cycle questions you have, Hess's law stuff. If you want to go over this again, we can. And then you've got a few questions to answer that cover all of the enthalpy cycles.